Good morning.
Good morning, sir.
Yes. So today we have around 19 students on board. Let's begin. So yesterday we were discussing about the kinetics, the enzyme kinetics. So there we have seen the uh, nature of the graph, what you get when you are varying the substrate concentration and what is the effect onto the enzyme activity. So as I told you that there were three assumptions which were taken into consideration. The first one is the pre-steady state, where you calculate the initial velocity. Then you have the steady state, where we consider that the reaction is in equilibrium. Okay, that is the rate of formation of the enzyme substrate complex is there. And the third one is that the saturated point, that is the maximum velocity, a point where all the active sites of the given enzyme has been occupied uh, by the substrate. So considering these three assumptions and combining them and going through the different mathematical or the statistical rearrangements, we come to the equation of the Michaelis-Menten. But if you look at the graph of the Michaelis-Menten, you get an hyperbola, okay, which shows that initially there was an increase into the rate of reaction, but then as the substrate concentration it goes on increasing, the increase is not up to the level what is expected, so it goes on decreasing, and maybe at one particular concentration you start getting a plateau region. So theoretically when we speak, you get that plateau region. Okay. But practically you may not get a constant velocity for that particular reaction, because even though the active sites are occupied by the substrate is going to be converted into product. So the active site is free, new substrate can come and bind. So some or the other kind of the activity might take place in that particular condition of the maximum velocity. So you may not get an exact plateau what is expected. Okay, and that becomes a hurdle in case of the Michaelis-Menten plot or the equation, that you cannot calculate the accurate value of the maximum velocity, that is the Vmax. Okay, and if you are not able to get the maximum velocity, you cannot calculate the Km. Okay, so these two terms, they are very important when you are talking about the activity of the enzyme, and for that reason there were some modifications which were done into the Michaelis-Menten equation. Okay, and it was converted into a form that is y is equal to mx plus c, so that you can plot a graph which is a straight line. Okay, and whenever you have such kind of plots, you are supposed to get the accurate values for your entities, fine. And that is what is done into the LB plot, then the Halden plot, and one more modification is there. So in these three plots you have the ability to calculate the accurate value of the maximum velocity, and if you know it, you can calculate the Km. Now the next question comes, that what is this Vmax or the Km? How do you define them? What is their exact applicability? Vmax, as I told you, it relates to the velocity of that particular enzyme. Why it is called as maximum velocity? Because it is the state of the enzyme where all the active sites of those enzymes are occupied by the substrate. Okay, now here a given enzyme can have one active site, a given enzyme can have more than one active site. We are not sure about it. So here what we are saying, that in case of Vmax, all the possible active sites in the given enzyme molecules are occupied by the substrate. That particular condition is called as the saturated condition or the maximum velocity. Okay, so this maximum velocity will help us to understand that what is the rate of the particular reaction. If a given enzyme is reaching its maximum velocity at an early stage, so you can say that it is a very efficient type of an enzyme. Okay, so this is how you can correlate it. The next thing, it comes the Km. Km, as we have defined, that it is the substrate concentration at half the maximum velocity. But what actually this Km gives us an idea. So roughly what we can say, that this Km, it helps us to understand the affinity between the substrate and the enzyme. Okay, so more the affinity, more the possibility of formation of the ES complex, and higher will be the rate of reaction. Although this concept of affinity may not be true for all the enzymes, that is why I'm using a word that is roughly. So roughly you can define that Km can be related with the affinity of the enzyme towards the substrate, right? So knowing this, what we can say, that lower the Km value for a given enzyme, okay, lower Km value means what? It is having a very high affinity for the substrate. So lower the Km, higher is the rate of reaction. Okay, so that is what is the applicability of these two terms, that is the Vmax and the Km. And Km, as we know how we calculate, that it is nothing but the rate constant. So we have simply collected all the rate constants and we have tried to find out that what could be the rate of reaction in that particular condition. Fine. Sorry, there was an interruption. Fine. What I was talking about, yeah, about the Km. So it's related to the rate constant, or the you get an information about the rate limiting uh, factor in that particular equation. But now, if your given reaction is involving some more intermediates. See, we have considered an equation that is E plus S is forming only the ES complex, and directly it is converted into E plus S. But if your reaction is involving one more intermediate, like suppose the ES complex is first converted to EP, and then EP is converted into E plus S. So if the obviously the rate limiting step is going to vary. In the first condition, what we discussed, that about the ES is converted to E plus S. So we said that the K3 is a constant. But now your ES is getting converted into EP, and then EP is converted into E plus P. So you are having one more constant here, that is, you can name it as K4 now. Now here, the rate of that particular reaction, or the rate limiting step in this condition, is going to be your conversion of EP to E plus P. So what is the rate constant which is going to decide the rate of reaction? It is the K4. Right. So it depends upon that how many intermediates are involved in the given reaction, or which particular step of that particular reaction is the rate limiting reaction, that is going to vary for the different type of the enzymes. Okay, so to avoid this particular confusion about the rate limiting step, we have introduced a new term there, that is called as the Kcat. So Kcat, it indicates the catalysis for that particular enzyme. Okay, and that Kcat is relating to the rate constant, which is actually deciding the rate limiting step of that particular reaction. Okay, so to avoid that particular confusion, that how many intermediates could be involved, we are using simply a term that is called as an Kcat. So Kcat is nothing but the turnover number. Okay, now this turnover number means what? So turnover number, it gives us an idea about the rate of the reaction. Okay, that how many substrate molecules are converted into the product per unit time, okay, and per unit of the enzyme. Lakshat gya what I am trying to explain here. So this turnover number, it indicates that how much substrate molecules are converted into product per unit time and per unit of the enzyme. Okay, means the time you can take it into seconds to minutes to hours. And per unit enzyme means what I want to say here, that how much amount of enzyme you have taken, whether it was 1 nanogram, 1 microgram, gram, kilogram, etc., etc. Fine. So if you can put this relation, that this much amount of enzyme in a given time is converting these many substrate molecules into the products, is nothing but the turnover number or the catalytic power of that particular enzyme. Okay, so this is how we calculate the velocity. Fine. Now this kcat for a given enzyme is going to be unique. Okay, so each and every enzyme is going to have its own unique kcat value. But there are some reactions. Okay, there are some enzymes which act on different substrate. Okay, so they may have the different kcat values. Fine. Or you may take some example that just 1 minute. That there are two enzymes which are catalyzing different reactions, but they may have the same kcat value. That is the same turnover number. So again, here the confusion is occurring here. Okay, so to avoid that particular type of the confusions, where two different enzymes I'm talking, so they are catalyzing the different reactions having the kcat. In that case, we simply take an ratio of the kcat to km. Okay, and then you can now introduce one more constant here, that is called as a specificity constant. So kcat upon km is nothing but the specificity constant. Okay, so that is another term which will help us to understand that how much efficient is your enzyme. Now, knowing this, one more factor which you have to take into consideration about the solubility of that particular enzyme and the substrate. Okay, and we have an idea that most of the enzymes, they are soluble into the water. Okay, so that solubility can be related to the specificity constant, right? And what it has been found, that majority of the enzymes have their specificity constant which is similar to that of the solubility into that particular environment, right? And it is in the ratio of around 10 raised to 8 to 10 raised to 9, right? So if you refer to Leninger, there is one uh, table which is given, because this question was asked by Nupur. She had a problem that she couldn't understand that particular table, but simply it is giving us the information between the kcat to km, means what, the specificity constant for that enzyme, the catalytic power of that enzyme, which can be correlated with its solubility into that particular environment. Okay, and that environment is the aqueous environment. Whenever I'm talking about environment, you have to take into consideration that we are talking about the aqueous environment. So if your enzyme is soluble, then only it can act upon the substrate. Okay, so that solubility, or the diffusion control limit, it is called as, so that diffusion control limit is close to the value of the kcat to km. Okay, so you refer that particular table, and there you can get the ratio, and from that you can understand that how efficient these enzymes are. Okay, so in that the first enzyme what they have given, that is acetylcholine esterase, it has a kcat value of 1.6 into 10 raised to 8, right? So these are few of the terms which you will have to keep in mind. Say for example, kcat, which I told you. So before that, the Vmax you should know, then the Km, then you should know about kcat, that is nothing but the turnover number, and then you should also know about the specificity constant, which is nothing but the kcat by Km. Fine. Now these are the terms which we are trying to understand. Okay, when there are some different conditions which come into existence. Okay, otherwise Km and Vmax is more than sufficient to understand. But under some specific condition, that whether the substrate is at a very low concentration or the substrate is present at a very high concentration, etc., etc. So in that particular condition, these things are going to change. Okay, so I think I have tried to give you some glimpses about this. We are not going in more detail about the kinetics, but these terms should be known to you if you are talking about the enzyme kinetics. I think it is clear. Nupur, you got it?
Yes, sir.
Okay, fine. So that is all from my side. Now we'll continue with the presentation. So I think who is it? Rajeshwari, no?
Yes, sir.
Yeah, so Rajeshwari, you can present your screen and start your presentation.
Okay, sir.
Yeah.
Am I audible?
Yes, you're audible. Your screen is also visible.
Yeah. Okay. Good morning, everybody. So today we'll be discussing the factors influencing the enzyme activity. Let us understand the first time when the term enzyme was introduced. It was in 1897 by Edward Buchner, and he uh, he saw that the fermentation of sugar to alcohol, this process was catalyzed by some specialized molecules, and he called these molecules as enzymes. Now we define enzymes as these are the proteins or biological catalysts which lowers the activation energy of the reaction, and helps in speeding up the reaction rate or regulation of the rate of reaction. So even though these enzymes take part in a chemical reaction, they are not consumed in the reaction. Like we see over here in this slide, the green molecule is enzyme. It has an active site where the substrate molecule binds. Uh, where the substrate molecule binds. The enzyme and substrate molecule, when react with each other, they form an enzyme substrate complex. This reaction is then catalyzed because of the enzyme, and we get a product which is bound to the enzyme. After some time, after the formation of enzyme product complex, the product is then separated and enzyme is separated. It is not altered in this reaction. This is the function of the enzyme. So this rate of reaction is affected by various factors like the concentration of substrate, concentration of enzyme, the accumulation of end products, temperature, pH, water, and many more. Let us discuss these factors one by one. The first factor which we are going to discuss is the concentration of substrate. In the media, the higher the concentration of when we increase the concentration of substrate, it will increase the speed of the reaction, since all the active sites of enzyme will be occupied. Uh, since all the active sites of the enzyme will be occupied, the rate of reaction is going to increase. But after a particular period, upon increasing the concentration of substrate, it is going to saturate, and this saturation will cause the after a particular point, this saturation will decrease will have no effect on the enzyme activity. As we see over here in the graph, when we plot the graph of rate of reaction versus substrate concentration, we get a hyperbolic curve, and we can see that after a particular point, the rate of reaction is constant, even if the concentration of substrate is increased. The second factor which will be affecting the enzyme activity is concentration of enzyme. It is same as the concentration of substrate. The small amount of enzyme is enough for large amount of substrate. Therefore, an increase in concentration of enzyme will thereby increase the rate of reaction. And when we plot the graph of rate of reaction 1z versus enzyme concentration, it will be same as the hyperbolic curve. The increase in concentration of enzyme will have a specific effect on inhibitors. Will have a specific effect on inhibitors. Can anybody tell me, if we increase the concentration of enzyme, what will be effect of inhibitors in the media?
It will be directly proportional.
No, if we increase the concentration of enzyme, the inhibitors will have less effect.
Here it will depend upon the type of inhibitor.
Yeah, the competitive inhibitor
Yes.
it will be less.
Yes.
So it is same in case of concentration of substrate. When we increase the concentration of substrate, the effect of inhibitor, the competitive inhibitor will decrease.
Okay.
The third factor affecting the enzyme activity will be accumulation of end products. As the reaction proceeds and end products are formed, the product starts to accumulate and the activity of enzyme starts to decrease. Since the active sites of enzyme start to get crowded with the product, the rate of reaction will decline because the substrate molecules will have less chance to bind to the active site. This inhibition, which is caused by the end products, is also called is a regulation mechanism of enzyme, which is also known as a feedback inhibition or allosteric modulation. The next factor will be the temperature. When the temperature is increased, the kinetic energy of molecules is also increased. This causes the highly energetic collisions of molecules, and thus the rate of reaction increases. At lower temperature, the activity of enzyme is also low. Most of the enzyme uh, most of the enzyme have maximum activity at the in the range of 30 to 45 degrees Celsius. Above 45 degrees Celsius, the enzyme activity is drastically reduced, and beyond 60 to 70 degrees Celsius, the enzymes will show no activity since they are denatured. The rate of reaction, here we can see it is a maximum. Here we can see that the rate of reaction is maximum at the optimum temperature. This After a particular point, that is the optimum temperature, the rate of reaction will decrease since the enzymes are going to denature. The next factor we will be discussing will be the pH. The enzymes are active only over a limited range of pH, and most of the enzymes are specific to a particular pH. For example, trypsin, it is active in alkaline medium, diastase, it is active in neutral medium, and pepsin, it is active in acidic pH. So every enzyme it will have an optimum pH where the velocity of reaction is maximum. Each and every enzyme has a particular range of pH, and it works in that limited range of pH. So when we plot a graph of rate of reaction versus a pH, we get a bell-shaped curve. As we can see over here, the three enzymes pepsin, salivary amylase, and alkaline phosphatase are plotted over here. We can see that the optimum pH of pepsin is in between 2 2 1 1 and 2. So we'll see that the rate of reaction of pepsin will be maximum in the range of pH 2, and after pH, if we increase or decrease the pH, it will drastically reduce the rate of reaction. Same in case of salivary amylase. The optimum pH of salivary amylase is 6, it is in between 6 to 7. So after the pH increases, after if we increase the pH of medium after 7 or 6, the rate of reaction is going to reduce. And same in case of alkaline phosphatase. The hydrogen ions in the medium influence the ionic charges on the amino acids and in the enzymes, and particularly on the active sites. Thus, this affects the rate of reaction in the enzyme. It affects the rate of reaction of enzymes. We have to keep in mind that the pH, the rate of reaction, will be highest at the optimum pH of the enzyme. The next factor is activators and inhibitors. Let us first discuss activators. So, the addition of activators will enhance the activity of enzyme. The role of activators is to enhance the activity of enzyme. When the prosthetic group, which is organic metal ion, it when the prosthetic group which we add in the medium, it is an inorganic metal, it is a cofactor, and when it is an organic vitamin, it is called as coenzyme. So the when we add activators in the medium, it will enhance the activity of enzyme, and thus it will the thus it will indirectly affect the rate of reaction. Inhibitors, the role of inhibitors is to reduce the enzyme activity, and the when enzyme the inhibitors when the enzyme activity is reduced in the presence of inhibitor, when enzyme upon substrate concentration is increased, these inhibitors are less. That is, we have discussed it. When the concentration of enzyme or concentration of substrate is increased, the competitive inhibitors will be nullified. The activity of inhibitor will be nullified. So there are three types of inhibitors, which is competitive, non-competitive, and uncompetitive. So non-competitive inhibitor, it is a type of inhibitor in which the enzyme will have the active site. The inhibitor comes and binds to the enzyme other than the active site, but it binds to the enzyme and changes it brings a conformational change in the enzyme, which does not allow the enzyme to bind to the which does not allow the substrate to bind to the active site, and the reaction rate will be altered since enzyme cannot bind to the active site. Substrate cannot bind to the enzyme active site, sorry. The second type is the uncompetitive. In uncompetitive inhibitor, in uncompetitive inhibitor, the substrate can normally bind to the active site of enzyme. This inhibitor is not at all is not competitive, and thus it does not have any effect on the binding of enzyme and substrate. The next type of inhibitor is competitive inhibitor. In this case, the enzyme mimics the in this case the enzyme inhibitor mimics the substrate and competes for the active site on the enzyme. It is This type of inhibitor is called as competitive inhibitor. There are various other factors such as water, radiation and light, time, etc., which also affect the activity of enzyme. Water, the enzyme activity is suppressed in the absence of water. Water provides a medium for enzymatic reaction to take place. Therefore, water is a factor which will be affecting the enzyme activity. The radiation and light. Some enzymes are sensitive to light, while some require light for its activity. Example, photolyse enzyme. It is involved in photoreactivation DNA repair. Uh, In influence of harmful radiation like X-rays or gamma rays, the enzyme activity is decreased. These radiations form peroxides, which will cause the oxidative stress, and this will cause the oxidative stress. Thus, the radiation and light is going to affect the enzyme activity. Thank you. Any doubts?
Yes, any questions? Okay. Rajeshwari, a good presentation.
Thank you, sir.
Yeah. But still, I wanted some more details where now we'll have a discussion for around 5-10 minutes that what actually happens when there is a change in pH or temperature. Why is that in both the cases you are getting a bell-shaped graph? What does it actually indicates? That maybe the question can be that why at one particular temperature or at one particular pH your enzyme is showing the maximum activity, while on both the sides of the that particular point you have a decrease into the rate of reaction. What could be the reason? Yeah.
Sir, in pH, when the optimum pH, suppose if it is like a salivary amylase, its optimum pH was 6,
Hmm.
and we know that after its optimum pH, the optimum pH is the range where the enzyme works efficiently. After that, it doesn't work. So if enzyme is not working, the reaction rate will definitely will be hampered.
But my question is that why it is not working? What could be the possible reason at molecular level? Means as a general person, I understood what you want to say. You are just concluded that why the what does the bell shape graph tells you about. But I want at molecular level what actually happens. Why is the enzyme not working? Why there is a decrease into the rate of reaction? Maybe I want an answer from someone in the audience. Sakshi? Yes?
Yes, sir.
I want the answer for that question. Come on fast. Tejal, are you there?
Yes, sir.
So what could be the possible answer for it?
No, no, sir.
No? Shraddha? Yes?
Don't.
If everyone is going to say how it is going to help out, at least you have to try. You have to try, say, just speak some words. This is not going to help at PG level that you simply say yes or no. Nikita?
Yes, sir.
Hmm. Sonam? No? Pradnya?
The enzyme denatures.
pH? How it is going to denature? Means you are not trying to apply your mind. Whatever the logics we have learned up till now, you have to apply it here. Try to think. Don't be superficial. Hmm? Yes, Rajeshwari, you want to add something?
So when we change the pH, it will affect the charges on the amino acid molecules, and the amino acids then it may be the shape of the enzyme along with the active site. It will change because of that, and even in extreme pH, the enzymes denature. So that may affect the enzyme the rate of reaction.
Okay, fine. Uh, Somewhat what she has answered. Uh, okay, can you see my screen, the jam which I have? Can you see it?
No, sir.
No?
No, sir.
Okay, fine. Yeah, just for that, let me present. Okay. Yeah, see what we have talked about is the complementation between the enzyme active site and the substrate. See here, mentioning the active site is very important. Now, what is this active site? Active site, it is made up of some residues. Okay. So this active site is made up of some amino acid residues whose R groups are exposed in that particular region. Say for example, I'm trying to draw. I think the screen is visible.
Yes, sir.
Yeah. Say suppose this is the active site. Okay. So this is your complete enzyme. This is the active site. Now this active site, you have some functional groups. Okay. And these functional groups are the one which helps in interacting with the substrate. Now there is a complementation with respect to the shape, size, etc., etc., also the charges. So suppose this active site is having a negative charge here, a negative charge here, also you have a positive charge here, again a negative charge is there, and you have a positive charge here. So suppose this is your active site, which is the functional site. Now a given substrate which is having complementation with respect to these charges. Maybe at this point it may be having a positive charge here, it may have positive here, negative here, negative here, negative. Okay, and if a given substrate which is having the charges exactly opposite to these charges present into the active site, then only the complementation will be there. It will go and bind into this active site, the enzyme substrate complex will be formed, and the reaction will take place. But now when you are changing the pH, see what is going to happen. We have seen in the initial lectures that if there is a change into the pH, the amino acid is going to change its nature. That is, it can exist either in the cationic form, the anionic form, or the zwitterionic form. Okay, so whatever the functional group which is there, it is going to change its nature. So if I'm changing the pH, what is going to happen? That this negative charge in the active site may be converted into positive. This may be converted into positive, and wherever there was positive, it may be converted into negative, because all the amino acid residues have a difference into their behavior with the change into the pH. If the charges within the active sites, if they are changed by the change into the pH, the enzyme, it loses its complementarity with the substrate. Okay, and that is why at a given particular pH, the enzyme active site is having all the charges, okay, having some specific charges which are showing complementation with the substrate molecule. Okay, so now you can start imagining that if you are changing the pH, maybe if you are in the example what she quoted about the amylase, that it is showing an optimum or the maximum activity at an pH that is 6 pH. So below 6 pH, so somewhere between 5 pH, 4 pH, what you can say, that maybe the active site is getting cationic charges, and that is why the substrate cannot bind. Or maybe if I go above 6 pH, maybe the active site is trying to get the anionic charges, that all of them they might be having negative charges, so the substrate cannot bind, right? So that is the reason at molecular level that the charges within the active site are going to change if there is a change into the pH. Okay, and that is going to affect its binding towards the substrate. So this is what is expected at this level by understanding the basic things. Okay, so I think all of you got the point, that why you are getting a bell shape diagram or a graph when you are trying to study the effect of the pH onto the enzyme activity. The same thing could be for your temperature also. Now obviously, in case of temperature, we know that the enzymes, they are protein in nature. So protein, they are highly labile to the change into the temperature. Okay, so if you go on increasing the temperature maybe around 40-45 degrees Celsius to 50-55, so there you can say, yeah, that the enzyme is getting denaturing. Okay, because the residues are trying to move apart, the active site will be lost, and you will lose the enzyme activity. But then my question could be that if I go below that temperature, optimum temperature, where you are trying to decrease the temperature, there I can say, yeah, there has to be a higher possibility of having more and more non-covalent interactions. Okay, so the enzyme activity should increase, but that it's not happening. Why? Because if you remember, I told you that suppose this is your enzyme having an active site. This enzyme within the active site, although it has the charges, but these charges are not open. They are always solvated with the water molecules. So I told you that always the water is present between the enzyme and the substrate. So if you are going on decreasing the temperature, what is going to happen? The water will be having more and more number of hydrogen bonds within the active site. Simply remember that when you move from the liquid state of water toward the ice, there I told you that there is a maximization of the fine. So the possibility could be that at lower temperatures, the water, it remains tightly bound to the active site, so the substrate cannot come and bind. Okay, so the complementation may not take place, and you may not get the maximum enzymatic activity at the lower temperature, right? And that is why all these enzymes at a particular temperature, or specifically at 37 degrees Celsius, which is the temperature of our cells, at that particular temperature only, they have the highest ability to show the maximum velocity. Okay, and below that or above that, you can see that there is an change into the behavior, or you can say that there is a change into the enzymatic activity. Okay, so it slowly goes on decreasing, and maybe at around below 20 degrees Celsius or above 40 degrees Celsius, the enzymatic activity has been lost by that particular enzyme. Fine, and that is why you get that bell-shaped graph in case of the pH and temperature. Now, in case of temperature, one more thing which you can add, maybe I have told you about this. There is something called as a temperature coefficient. That whenever there is a change into the environment with respect to the temperature, the change in temperature is going to affect or change the pH of that particular solution. Okay, and that it is given by a term that is called as an temperature coefficient. So each and every molecule which is having the buffering activity will have its own temperature coefficient. Means what? That a change in temperature is affecting the pH. Means how much? So what it has been found, that if you change the temperature by, say, suppose 10 degrees Celsius. Okay, what I'm trying to say, that if you change the temperature by 10 degrees Celsius, the pH is going to change by 1 unit. Okay, say suppose you are working at 40 degrees Celsius. So at that particular point, your pH was around something 6.5, where your enzyme, your system is working very fine. But now you are changing the temperature, maybe from 40 you are moving to 30. So if you have moved from 40 to 30 degrees Celsius, obviously it has caused a change into the pH of that solution. So in that case, there is a possibility that this 6.5 can be changed to 5.5, or it can be changed to 7.5. So your temperature is also changing. It is affecting the pH. That is, the pH is also changing, and that change in pH is again going to add upon the change into the charges at the active site, right? So whenever you are talking about the temperature, you have to talk about also the change into the pH, which is going to change the nature of your active site. And if there is a change into the nature of your active site, it will change its complementarity towards the substrate, and obviously it is going to affect the enzymatic activity. Okay, so Q10 is nothing but the temperature coefficient. So a change in 10 degrees Celsius is going to change the pH by 1 unit. So these are the things which you are supposed to apply and try to explain whenever someone is asking you about the effect of enzyme activity uh, by the pH and the temperature. Is it clear? Any doubts into this? Yes, Rajeshwari, you got it?
Yes, sir.
What about others? Shraddha?
Yes, sir.
Okay. So the same way you can imagine now that what the how the time is going to affect, then how activators it is going to affect. So those particular things you should be aware of. The next what she has tried to explain is about the inhibitors, and it's a very important thing. I'm doubtful whether it is giving your syllabus or not, but you try to read that particular region where these inhibitors has been talked about. So she brought about the three types of inhibitors. They are called as the competitive inhibitor, the non-competitive inhibitor, and the uncompetitive inhibitors. Right. So all these three types of the inhibitors, they have the variation in the nature of their effect, what they are causing into the um, enzymatic activity. But all these three types comes under a category that is called as an reversible type of the inhibitors. Maybe by some or the other reason you can reverse the effect of this inhibitor. There is one more another type of an inhibitor that is called as an irreversible inhibitor. Means that irreversible inhibitor is having an covalent type of interaction, and there the example can be quoted that cyanide. So cyanide, it will go and bind to the cytochrome oxidase complex of the electron transport chain, and the person may immediately die. So that's an irreversible type of an inhibitor. While these three types, competitive, uncompetitive, non-competitive, they come under the category that is reversible, where they are involving the non-covalent interactions. So they can be reversed. So in case of the competitive inhibitor, if you go on increasing the substrate concentration, obviously the chance of the enzyme to interact with the substrate will increase, and you can reverse the effect of the competitive inhibitor. The same way the other two type of the inhibitors can also be diluted, or the effect can be lessened in that case, right? So just read out those particular chapters, uh, make a note of them with some representative example of each type. So you should be aware of that particular type. Now within that, one more thing which you can add upon, that if you are given a particular molecule and told that this is an inhibitor, now how will you identify whether the given inhibitor is a competitive type, a non-competitive type, or an uncompetitive type? So here you have to do the experiment uh, of changing the substrate concentration, and to that you are adding an equal amount of the inhibitor, and you are doing the experiment. You plot a graph, and that graph could be similar to that of the plot, because you are working on a parameter called as in substrate concentration, so you get an plot. Now by adding the inhibitor, Depending upon which type of inhibitor is there, you may see the change into the graph of the plot. Okay, but as we know, plot is not going to give you the exact or the accurate values, so we convert those particular plots into the LB plots. Okay, so you can see in the book they are given three types, three variations into the LB plot. So in case of competitive, you may get the plot where I think in that case it is the Vmax which remains constant, but the Km is going to change due to the addition of the competitive inhibitor. In case of the non-competitive inhibitor, it is the Km which is going to remain constant while the Vmax is going to change. And while in case of the uncompetitive inhibitors, you can see that both the Km and Vmax, they are changing. So depending upon your experiment and the plots, whether you are getting Km which is constant, whether you are getting the Vmax which is constant, based on that, you can classify, or you can segregate, or you can identify whether that given inhibitor is an competitive inhibitor or a non-competitive inhibitor or an uncompetitive inhibitor, right? So for that particular purpose, so you read out that chapter of the enzyme inhibitors, try to have all these points into your notes, and that will help you out in your uh, maybe for exams also it will be helpful, or for some other purpose if you are interested, right? So that is all from my side. So I think all of you have understood this particular point about the factors which are going to affect the enzyme activity, right? So we'll stop with this particular point. So tomorrow I think we have some 2-3 people who will be talking about the applications in the different fields, so we'll try to listen them. It's my request to all of them to have more and more examples. Okay, so it's good that you put on more examples and try to explain that what are the different applications of these enzymes. So let's see what they are going to tell us, and then we'll discuss if things are required, I'll discuss on to that particular point. Fine. So please write your roll numbers in the chat box. Yeah. Komal, can you please write down the roll numbers and send me?
Yes, sir.
Yeah. Fine. So if any questions are there, you can ask me, or otherwise we'll call it for a day. In between somewhere we'll have 1 or 2 exams, because we have covered a lot of portion. So maybe we can have some exam. I'll think upon it and I'll let you know. So you start studying for those particular points. Okay. So she might have finished with writing the numbers. We'll call it for a day. Good day, all of you.